FALL18FuelCellBattery. Our advisor is Professor Wang, and my name is Chris.
My name is Li Xin.
My name is Yi Heng. My name is Victor.
So these are the general outlines that we're going to go through today. I'll be introducing the background and some of the progress that we've made and budgets and resources, and we're going to end with the sub-team breakdown. So as far as the background is concerned, this graph is showing the past discoveries of fossil fuel and the rate of consumption. And based on this trend right here, we see that because of limited supply and increasing demand, someday we're going to have shortage in fossil fuel. And this graph is showing the emissions caused by burning fossil fuel, such as gasoline, methane, natural gas. And with this graph, we see that with an increasing consumption rate, we're going to have the increase in the polluting criteria. With this issue, I think fuel cell is the next energy production device, because with fuel cell, especially with proton exchange membrane fuel cell, the fuel cell is operated by pure hydrogen. And the good thing about injecting pure hydrogen is that water is the only byproduct. And with zero pollutant emission, because there's no carbon molecule within the fuel, and then the temperature is relatively low. The operating temperature is relatively low, so we don't create NOx. And the good thing is that fuel cells are generally more efficient than combustion engines, because fuel cells are not restricted by the Carnot efficiency, whereas because it is not restricted by Carnot efficiency, but it's restricted by the change in Gibbs energy, which is determined by the electrochemical potential. And as far as the sustainability is concerned, hydrogen is abundant. You can find it anywhere, but it's abundant, it's out there, but we have to somehow separate hydrogen from other sources such as water. And I think electrolysis is a good way to separate hydrogen from water. There are a lot of research, there are a lot of ongoing research that shows how, to see how efficient electrolysis is and how we can separate hydrogen with using solar energy. There's also another research that Professor Brau is doing on using curtailed wind energy to separate hydrogen from water using electrolysis. So I think that as technology develops, I think we can have both renewable and sustainable energy.
So as for the goals and objectives for our fuel cell battery, and we have two main goals this whole year. We need to achieve the Department of Energy 2020 targets, and which is maintain the 0.8 volts at 300 milliamps per centimeter square. And we also need to achieve the living current density, which is about 1.5 amps per centimeter square. And these two pictures shows here is our fuel cell that we have. And this is the test station that we used for testing. And we set some requirements for our sub-teams. And for the manufacturing, we hope that they set the limit for the bipolar plates and also the channel depth. And we want our porous media, the porosity is greater than 80%. And we hope that the heating pad could only take 10 minutes to heat our fuel cell from 20 to 80 degrees C. And as for the modeling and simulation, we hope that we can generate a model for the polarization curve and keep that within 50% with our data points. And for the testing team, they have to set the requirements for the MEA, and they need to calculate the flow rates based on the desired limiting current density. And before they can take measurements, we hope that we can achieve our open circuit voltage greater than 0.9 volts, because that's the minimum requirement for the PAM fuel cell. And for the timeline this year, we hope that we can finish our design and manufacturing by the end of week 9 this quarter, and just do some testing and reach a limit current density, which is nearly about 600 milliamps per centimeter square. And head for the winter 2019, we hope that we can achieve 0.6 volts and 0.7 volts, both under the 300 milliamps per centimeter square. And by the end of the spring quarter, we hope that we can achieve those automated goals, which is maintain the 0.8 volts at 300 milliamps per centimeter square, and also the 1.5 amps per centimeter square for the limit current density. We have some progress based on our previous design. And this year, we're going to still use the stainless steel 304 bipolar plates, but this time we add flow channels in it, because we think that this will evenly distribute the flow, and it will make reaction efficient. And we changed the locations of the inlets and outlets. Previously, it's on the side of the bipolar plates, but this time we changed to the top and bottom, so that we can directly connect to the test station. We can solve the problems of the condensation of those intermediate tubing. And we changed the fasteners holes. Previously, it's like parallel, 3 parallel plate, and this, no, sorry about that. And this time we changed to circular pattern, and it is easier for us to attach the heating pad, and also it's easier for us to seal the fuel cell. And we have 2 manufacturing options. The first is we will send all the parts to the tuckers, and then he will do all of that, but it will cost more. And the other is we do the drilling and drilling the fasteners, and then only let Tucker do the inlet and the exit holes and also the flow channels for our fuel cell, because those are more precise. So I will hand my presentation to my colleague.
So we, just like the manufacturing team, our simulation team has made some progress. So this quarter, as of now, we came up with what we researched on the polarization curve, which is a function of the Nernst potential, activation, ohmic, and concentration loss. And this is the general equation for activation loss, where these are all constants found by some of the engineers that published journal articles. And this is the relationship for the ohmic loss, where it's a function of both temperature and activity of water vapor, which I'll explain that in the next slide. And this relationship here is for the concentration loss, so which is like basically the function of temperature and the concentration of oxygen at the anode and concentration of oxygen at the exit, and the binary diffusion coefficient, and that is the determining factor of the limiting current density. So right now we're working on getting the porosity and tortuosity of the membrane. There aren't many experimental values, so as of now we're just using just the constants that others have used, but we hope to specify these 2 parameters for our membrane. And these 2 are the polarization curve generated on MATLAB. So on this graph, we set the relative humidity as constant at 100% and vary the temperature from 300 Kelvin to 350 Kelvin. And as you can see, here, I think this higher temperature leads to higher Nernst potential because of the Arrhenius activity. Because of higher temperature, we get higher voltage, but yeah, and then you can, as you can see here, as we vary the temperature, there is an effect on the ohmic loss, which is this here, the linear region right here. And this curve, we set the temperature constant at 350 Kelvin and vary the relative humidity from 100% to 50. And this is quite interesting because we would think that higher humidity, higher relative humidity will result in better polarization curve, better efficiency. However, when we use 100% humidity, relative humidity, we get lower current density. That's because the water accumulates at the exit of the fuel cell, which limits the activity due to a limitation of mass transport. So based on this two, and then we hope to actually validate this two curve with our own testing fuel cell. So that's our next quarters and spring quarters goal.
Okay, now I will show you guys some simulation we've done so far for our new design flow channel. So when we finish our CAD model, we plug it into the ANSYS fluid. By using these simulations, we can easily determine the pressure distributions and flow streamline profile for our new design, which is very important because the concentrations and activities of the reaction inside the fuel cell are closely related to the pressure. So as the first picture showing, first we meshed our flow channel model into around 80,000 meshing elements. Then we simulate the pressure distributions at the interface, which is shown in the middle picture as the rectangular area. And it is the approximate pressures of the reactants at reactant site. So by doing these simulations, we can make qualitative assumptions that if our fuel cell, for our fuel cell performance, and as well we can verify if it generates desirable pressure distributions that can meet our overall requirement, which is 0.8 volt at the current density of 300 milliamp per centimeter squared.
Okay, for the budget, our total budget is $3,000 for this year. And the estimated cost of the materials, including all of the plates and the tubes and the fittings, is about $4.50 and 22 cents. And the estimate for the manufacturing, there are two options, like just this inside. The first one is Tucker will do everything, and the estimated cost is about $325. And the second option is that the Tucker will only do the inlet and exit hose only, and it will cost like $183. And for now, we only purchased the snoop for the gas leakage detection, and it costs $10. And the resources, here is how many units and how many hours our team members are taking. And we can get some resources from the Renewable Energy Resources Laboratory, where is the location we are working at. And we can also get some other resources from the National Fuel Cell Research Center. And here's our subsystem breakdown. And Professor Wang is our advisor to help us finish the project. And two team leaders, the technical lead and the logistic lead, Lixian and Eddie. And there are three teams in our project, manufacturing team, testing team, and the modeling and simulation team. And there are 13 people in total in our project. Okay, we hope we can finish our goal and the timeline. Thank you for listening.